Okay, so let me finish now this last hour of the last afternoon of this school. Just want to say a few words before I switch to flame wall interaction, to this question of the spark modeling. Again, the spark modeling, it's an extremely complicated problem, and in 3D codes, we just cannot hope to capture everything which is really taking place during these plasma phases. And in most cases, what we do is there are two solutions. In most cases, we just replace the ignition by something which creates energy in a sphere, which is what I've done in most cases. Or you can even wait a little bit more, say, okay, whatever energy I do at the end of the ignition phase, what I have is a kernel of burned gases with a temperature which could be more than the adiabatic flame temperature if you have a very strong spark. And those are the two methods you have in most codes. But you have to realize how simplified those things are compared to a real ignition event. This is time in log scale, and you see this is the voltage going through a spark. This is the intensity. So the power is extremely complicated here. The deposition of energy is very complicated. And we replace all that by a very simple model. So you should not expect too much of that. In other words, if the ignition phase is not important, the models are okay. If the ignition phase is critical, this part here today is really much too simple when you replace it with a model like this. This model is what we use when you deposit energy. So we start with a cold flow, we add energy locally, temperature goes up, and when temperature is right, then you go into ignition. So this is an example of this sequence. You have the temperature. Here the blue was the spark. And you can see here that even with a simple model like this, it's a complicated story. Okay? Now the flame is almost established. You have the temperature here. You have the two peaks of reaction rate on both sides. Okay? Again, to come back to the discussion we had a long time ago, look at the scales here. We're talking about flame fronts, which are, this is meters, this is millimeter, this is a few fraction of a millimeter. There's no way you can capture that if you don't have the mesh to do it. Huh? So same thing again, you deposit energy, hop, and then you stop. Temperature has gone up enough. Then chemical reactions begin. You have here the two shock waves going away. They're not shocks, actually, they're acoustic waves. And then finally you ignite. Okay? So it's even without the plasma phase, it's a complicated story. All these questions here are still open questions. You know, do we really need to care about the details of all that? If you look at a real visualization of a spark, you see how complicated it is. It can actually, you can have a spark which stops and restarts again later. All these details, if they are important, we are in trouble. The minimum ignition energy has been mentioned before. This is the energy you need to deposit to create a sphere of burned gases. And you can evaluate it by different ways. The Zeldovich method mentioned by Paul is one, but there's an intuitive method to say that if you don't have here the place to put two flames back to back, there's very little chance that this thing will ignite. So you have a simple estimation here of how much energy you need. You need to deposit at least a sphere which has a diameter larger than 2 times the flame thickness, and which is hot enough to go above the ignition temperature T2. And this is close to the adiabatic flame temperature. So in one line, you can write the minimum ignition energy you need to put in the flow for it to go hot enough to start burning. And if you plug all that here, you find about 1 millijoule for typical conditions. Most sparks will deposit much more than that, like 50 millijoules. And the big problem is that a lot of the energy of the spark is lost, so you don't exactly know how much really goes to the gas. But those things are still coherent. We're talking about 1 to 10 or 20 millijoules. So this is a plot of the minimum ignition energy as a function of equivalence ratio. And of course, the minimum energy is reached when you are stoichiometric, and if you are lean or rich, then you need to put much more energy to ignite. And of course, if you are outside flammability limits, you cannot even ignite. Now, how much energy do you need to put in an electrical circuit of a spark to have 1 millijoule in the gas? Well, that depends a lot on the losses. And depending on who you're talking to, people are going to tell you that the losses are, there are many losses. A lot of the energy goes back into the electrodes themselves, which get warm, and a lot of it is lost by energy, by radiation. You can also, people saying that a lot of it goes to the shock wave, and we'll show a picture in a second, so that basically when you put 100 millijoule in your spark, you expect to find between 10 and 30 millijoule in your model, which is a big error. I mean, you don't really know how much you should put. So that's a problem. If you use a laser, experimentalists are in a somewhat better shape. They can give you a better estimate for what's going on in a laser. That's actually another result of the Princeton group. And in Princeton, the funny thing is that they show, for example, here that when you change the ignition energy, you get different flame shapes. So that's even a problem because the ignition phase seems to control what's happening later. It's easy to understand if the kernel here is at 4,000 K or at 2,000 K, of course, things will go much faster afterwards. Now, there's one thing I want to mention. Not everyone agrees on the ignition process. There's a group, a few people saying that if you visualize, this is the spark here, you see a shock wave around it. And some people believe that ignition in certain cases could take place not because the hot gases are ignited here, but because the shock wave increases the temperature, and that behind the shock wave you would have ignition, which would lead to completely different models. So I'm not going to elaborate too much on this. I just want you to remember that if you need to measure or to model the ignition phases, and if they are important, you have to probably be very careful there. Okay, let me finish now by flame-hole interaction. So this is a fun topic I want to describe. Now, the point about flame-hole interaction, as I said before, is that whatever you do with the flame, usually it will be surrounded by walls. So the problem of how does a flame interact with a wall is a critical one in many aspects, and it's not one which is discussed a lot by the combustion community. Okay, combustion community doesn't care too much about walls. I mean, the academic one. Of course, in industry, you do care. Why do you care? You care not only because the flames will touch the walls. You care because the walls will affect the flames. I will describe that in a second. And the walls will also control pollution, because if the flames get quenched near the wall, that means you will leave some unburned hydrocarbons near the wall, and these unburned hydrocarbons can then leave and go into the exhaust gases in a piston engine, for example. In a gas turbine, you have another problem, is that the walls that we use in a gas turbine are usually multi-perforated. What we call multi-perforated, that means there are lots of small holes here, and those holes control the acoustics of the burner, which means really that these things will control the instabilities, which will change the flames, and etc. And like always, you cannot just separate these things. In a gas turbine, you have to worry about all these problems at the same time. If you change the walls to increase the cooling, you're going to change the acoustic damping, so maybe you will trigger instabilities. If you're an engineer and you talk to these people, quite often they tell you, I don't understand, I just changed the liner, which means the holes, and then suddenly my engine became unstable. It makes sense. It just comes from this loop here. But you have to have the whole picture if you want to understand what you see. Now, I will talk a lot about gas turbines, but actually the mechanisms I'm going to mention are general. You're going to find them in many other places. Let me just summarize an important property of combustion chambers. You go to a gas turbine company, and you say something like, combustion is very important for efficiency, and these guys are going to stop you and say, no, don't care. What's important for efficiency is the compressor, because the compressor gives you the maximum pressure, and the combustion chamber today, they all burn 99% of the fuel. So you cannot increase efficiency by increasing this aspect of the combustion chamber. You cannot burn more than 100%, okay? So if you want to increase efficiency in a gas turbine, you have to work on the compressor, not our problem. The combustion guys are out of this loop. Except that if the compressor is able to give you a higher pressure, what should not happen is that the combustion chamber must not do something stupid like making more pollutants. And that's easy to have this problem, because if the pressure goes up at the inlet of the chamber, the temperature goes up, so the NOx, is going to go up. So our role here is not, we are not leading this thing, we just should not stop it. So that means if the pressure goes up at the inlet, we must control the pollutant emission. And the most important thing is that when the pressure goes up, all the temperatures go up, and the walls may die. And that's, of course, not negotiable. Okay? So doing 1 is easy. We always burn almost everything. Doing 2 is not so easy, but doing 3, you cannot just say, I'm doing well here, okay? You have to do that. There's just no way. The engines must survive. If it does not, you get these pictures which I've shown before. Of course, then the show must stop there. Now, which walls are we talking about? In an engine, you have 2 types of walls. You have the casing, where you have what we call cold air. Be careful when you say cold, it means 700 K, okay? Not Fahrenheit, okay? And then in the engine here, you get more than 2000 K. And so you have your combustor walls here, which is the first problem. They must survive. And here you have the blades here at the outlet. They must also survive. So all of this has to be controlled. You cannot cool this thing with water. Every time you look at this picture, I see the piston engines people laughing and say, hey, you just put liquid cooling. You cannot do that in something which flies, okay? It's just, the weight would be too much. You can do that in a car. So you have to find a way to cool these walls with what you have. What do you have? You only have air, cold, what we say cold, 700 K air. So you must use this air to cool these walls, make sure they don't burn. And of course, you're going to use very fancy materials here, which can survive to high temperatures, but still, that remains, this challenge is extremely difficult to reach. And the temperature here, and especially here, is what controls the lifetime of the engine. You get this temperature wrong, and you melt the engine in a very, very short time. So this is a view which you've seen before. This is the reason why you have dilution jets here, okay? Here you get very hot gases, you mix them with cold gases so that at this point the temperature remains reasonable. But still we're going to have interaction between very hot gases and the blaze. And here on the side, on these walls, we're going to have something worse. We're going to have interaction between the flame and the walls. Now you all probably have done this experiment, you know, if you take a lighter and you can have your finger above the flame, and you know that if you go fast enough, you know, it's okay. If you stay, it's not okay. So you see, by the way, that flammable interaction is going to involve quite a few phenomena which are difficult to draw in 2 seconds. One of the first thing is, if you put any surface in a flame, the surface will receive a high heat flux. That's how you get burned. But the thing you don't really necessarily see is that when you do that to the flame will deliver high heat flux to you, so that means the flame will be cooled down also. And you remember that this was shown by Paul, any level of heat loss on a flame is not something that the flame likes. And if you cool it a little bit, then the flame dies. And this is what will happen at a wall. The wall will suffer because it will be heated by the flame, but the flame will die at the wall. And so it's the combination between the two that we need to study. Now, I want to eliminate the problem first, especially in many industry, the only way to cool the walls, that's what we do on the side walls of these engines here and here, is to use multi-perforated walls. So what's the idea of multi-perforated walls? Let me show you how this works. Okay, it will come later. Let me just clear this thing first. I'm not going to consider walls which burn. If you're not doing well, the temperature of the walls comes up. At some point, the wall either melts or burns. There are cases where you do that on purpose, but I'm not going to discuss that. The wall must remain reasonably cold. Reasonably cold means not really hot. If you look at a piston engine, the walls are not at 1000 K, okay? They are cooled with water, so you keep them reasonably cold. In a gas turbine, they are much warmer than that, but still, they don't burn. If you look at rocket engines, some people on purpose design, for example, carbon-carbon nozzles which burn, because it's the only way to allow this thing to work. It's not what I'm going to do here. So let me go back to multi-perforated walls. If you're an engineer, you need to cool these walls. You can say, okay, a good solution is to have small holes here and to have some cold air, 700 K, come here and protect this wall. So you create a film, we call that effusion cooling. We create a film of cool air between the combustion products here and the walls. And you realize that if one of these holes gets blocked, the film may be too thin, then the combustion products touch the wall and you're gone, okay? Which really means when you fly in an aircraft, your life depends on thousands of small holes like this, which protects the wall of your chamber from the combustion products. It's a scary idea. That's the picture of an helicopter chamber. Those holes are here, okay? Each of them is a small hole. So in France, we have people, children, drilling holes like this. It's a big job. So, actually, it's done with a machine. But the experience, for example, of Turbomeca is that they, probably 10 years ago, they changed the process by which they were drilling the hole. They drilled the hole with the same size, same length, but the shape of the hole was slightly different and the engine was not working anymore. Why is it so? It's because the details of every small flow here is important for the flux. And let me show you the simulation we did. This is one hole, okay? This is a DNS actually in one hole, so you have the cold air flowing here. You see actually you have separation in this tube. You create vortices, and so this is the film which is here. And you can see that, well, it's not an easy life, okay? You see it's fully turbulent flow. You have to do that for many holes, and you have to make sure that the film has a constant thickness, or at least enough to prevent the hot gases from hitting the walls here. So if you go talk to people in gas turbines, you will see they spend a lot of time on this problem of multi-perforation. It's an awful problem. One of the reasons being that you get in a typical chamber, you get 10,000 holes like this. So you cannot afford to do 10,000 computations like this. You have to replace that by some kinds of model. So I'm not going to talk about that. The stator actually of the blades can also be multi-perforated. We won't talk about that either. I want to stick to the simple problem of a smooth wall. Even for a smooth wall, actually, someone asked me the question 5 minutes ago, you still have the problem that if you do the computation of a chamber, you need to specify wall temperature. How do you get the wall temperature? Well, someone can give it to you. If you don't have it, the only solution is to solve for the temperature in the wall. So you do a coupled heat transfer simulation. And you need to discuss then how you couple the solvers. The LES solver in the chamber, and then the heat transfer solver outside of the chamber. And the acoustics I've mentioned before. So, depending on the time here, I think Friday evening, we're not going to stay too long. I want to discuss first the flame wall interaction, the general features, the things which are general that you should know about that. Let me just begin with the smooth wall here, and here there are flames. So what's happening? The flames are going to propagate toward the wall. And there are many ways that things can happen. If you are here on the wall and the flame is down there and here you only have cold gases, you're fine. Okay? So if it's non-reacting gases, cold gases, you have no problem. Now, if unfortunately for some reasons the burnt gases arrive at where you are, it's a heat transfer problem only. It's hot gases on the cold wall. But the worst situation is that if you're just at the point where the flame arrives, and so the reaction rate is right on you, then you have an even worse problem because you are located just at the place where chemical reactions take place. So those three situations can be mimicked here. If you take a premixed flame and you're sitting on the wall, either you are in the fresh gases, and here the flux is going to be low, reasonably low, let's say. You're going to have a little bit of radiation, but we are not going to talk about radiation now. If the flame comes this way, you are going to be in the hot gases, so you will be having a larger flux. And if you are just here when the flame touches you, then you have what we call flame wall interaction. And the flame wall interaction is the moment where the flux is the largest. Okay, that's the moment which is difficult. It's not going to last long. It's going to be intense. When we talk about orders of magnitude, you have to remember that the fluxes we reach in the flame are of the order of what you get in a nuclear power plant. We're talking about 1 megawatt per square meter. Fortunately, it doesn't last long, but it's a huge flux. Now, we can split the different situations where flames interact with wall. The first one, which is the easiest one to understand, is that you make the wall here. This is filled with fresh gases. You start the flame. It's a 1D process. The flame propagates. And when the flame will hit the wall, we have what is called head-on quenching. There's quite a few number of experiments on that you can find in literature. And people measure, not much actually, they measure the flux, usually the heat flux in the wall, to know how much you need to cool it. The second situation is when the flame propagates not in this direction, but in this direction, along the wall, and it's called sidewall quenching. And you will see that the situation between head-on quenching and sidewall quenching is actually different. So this is a movie I'm going to play just a couple of times here. This is a simulation of a flame in a head-on quenching configuration, hitting on a wall. And here you see the temperature in the gas, and here you see the temperature in the wall, but be careful, the scale is not the same at all. This is 10 K, this is 1500 K. You see, the point is that even with a flame, the inertia of a piece of metal is very large. When you send a flame like this one on this piece of metal, you heat up the metal by 10 K. Not that much, okay? We have a tool here which can compute this coupled interaction, as you can see here, but you could almost say that the wall is isothermal during the interaction. Of course, if you repeat that at 100 Hertz or 1000 Hertz, it's going to be a different story. So let's play this guy again. You see here you have the reaction rate, that's the blue line. You have the fuel mass fraction, and you have the temperature. So these things are all going this way, and you will see that the reaction rate will actually stop before it touches the wall. Look at the blue line. Whoop. It never reached the wall, okay? It died before. And then after it died, well, now we only have a heat transfer problem. Since the wall is cold, it has to cool down the gases in front of it. Okay.
There's no flow rate.
No flow rate. There's no flow. Actually, there is an induced flow rate here, but here nothing's moving. It's head-on quenching, no flow rate for the moment. So the way you post-process these things, if you do a simulation, if you just plot here the temperature profile, and you look at the distance between this point here and the wall. This is going to be called the wall distance for obvious reasons. And the wall distance decreases with time. And you see at some point the flame stops here because it's quenched. And the wall distance being defined by the position of the isotherm, which is here. After that, the flame seems to go away from the flame front, from the wall. Because if you look at this thing again, look at the temperature. It comes here, and then just because you are cooling the flame, this point here is actually moving away from the flame front. This is what we see here. So you have a straight line because it's a constant flame speed, and then poof, it quenches and goes back. Now, if you look at the flame speed itself, which is now the consumption speed, we integrate the reaction rate. When you're far away from the wall, the flame propagates as if nothing would ever happen to it. Okay, it hasn't seen the wall yet, and then suddenly it says, "Oh wow, this is cold." And it starts burning less, and it keeps, being pushed to the wall, and then it stops. It dies here. And at the moment where the flame dies, this is the moment where you get the largest heat flux to the wall. These things happen at the same time. So if you're on the wall, you have the same experience. You see this flame coming towards you, say, "Oh, wait a second," and then you get hit by the flame. You get all the heat flux, maximum heat flux here. But then, fortunately, the flame dies at this time. Okay, when the wall is cold. So you can scale these things now. That's what I'm going to do for you. You're going to see there are very simple theoretical results you can obtain from that. Here is the maximum wall heat flux through the wall, computed with different methods and with different experimental results. And here's the wall temperature. And this is what I was describing before. We're talking about fluxes of the order of 1 megawatt per square meter. That's the maximum heat flux. What you can do is you can look at these numbers and ask yourself, can I scale that? Well, actually, you can scale it in the following way. We know that the flame power is this expression. It's the heat released by the flame multiplied by the flame speed. That's the typical flame power. And you can actually scale the heat flux here, the maximum heat flux, by the flame power. And you find that's almost always of the same order. Of the order of 0.3, 0.4, 0.41, or something like this. except for hydrogen, but it's because hydrogen has such a large power. Now, what that really means is that when the flame touches a wall, it delivers about 1/3 of its power to the wall, and then it dies. And so you can keep this order of magnitude in mind, even if you don't know, this kind of tricky things to do, to show off a little bit. Give me your flame, I can tell you the maximum power that the maximum heat flux that any wall can receive because of this flame. And you see that the measurements actually agree pretty well. Of course, when you increase the pressure, the power will go up, and these numbers will go up. Now, there's a second thing that you can look at. It's the distance between the wall and the flame. And here, I've plotted it. It's the same plot I've shown before. The flame goes to the wall, and it stops here. And you can scale the distance where the flame stops, and we call it the quenching distance. What does it mean? It means that when the flame comes towards the wall, there's like a layer of a thickness equal to the quenching distance where the flame stops. It cannot go in this layer. And the quenching distance, you can scale it also with this famous flame thickness that we've used many times, which is the diffusion of heat divided by the flame speed. And again, when you do the scaling, you find that almost in all cases, the Peclet number, which is the ratio of the quenching distance by the flame thickness, is of the order of between 3 and 4. In other words, during head-on quenching, the flame stops at approximately 3 flame thicknesses from the wall. You cannot go closer. Which really means that the fuel which is left here is not burning. It's going to do something. Usually it diffuses into the burn gases. But in a piston engine, for example, you have crevices where the fuel can basically hide, because you have walls on all sides, and get out when the exhaust gases, the valves is open. And that's a process for pollutant generation. Okay, so remember that during head-on quenching, you never touch the wall, and you leave some unburned fuel, and that can be a problem for pollution. Now, what about sidewall quenching? Same thing, you can do theory also here, you can do simulation. You find out that it's the same process, except that the fluxes are less. Instead of 0.3, you find something like 0.15, which also means that the quenching distance is not 3 point something, it's more like 7. So when the flame propagates in a tube, there's a distance here where there can be no reaction. Again, if you do a simulation, you have to account for that. For example, you cannot simulate this problem with a code supposing that the flames are adiabatic, because obviously here, these flames are not adiabatic, they are cooled down. Why do they quench? They quench because this zone is cold, and I know it's cold, I cannot go there. I'm burning things with an exponential. If you decrease my temperature, I have to stop, so I cannot enter this zone. And if you have a turbulent flame, this is time here, this is reaction rate, this is vorticity. You see the flame coming towards the wall, you're going to have head-on quenching locally, and after you have head-on quenching, you're going to have sidewall quenching. So it's a combination of both. So when the turbulent flame hits a wall, and there's been quite a few DNS of that now, people have done it many times. We did this one 20 years ago, but you can find more sophisticated one in the literature. You're going to find out that the distance between flame and wall varies between Peclet equals 3 to 7 or 8. Now, the very interesting extension of that is the cases where you have a flame in a sidewall situation, sidewall quenching, but between two sides. Because then, you see the spore flame is propagating like this, but everyone is stealing heat from it. And if you steal too much heat from me on the right side and on the left side, at some point I'm going to stop propagating. Which really means that something that Paul mentioned before, if you steal too much heat from a flame from both sides, you're going to quench it. And that's what we call the quenching critical distance. And this critical distance, when you do experiments, you find that it's of the order of 50 times the flame thickness. Which really means that if you take a tube here, which has a radius smaller than 50 times the flame thickness, which is of the order of 0.5 millimeters, something like this, the tube, the flame will not be able to propagate through it. So that will be very important. The way we found that out is that initially when people were computing flame speeds, measuring flame speeds, everyone was doing flame speed in different tubes. Some people using a big tube, using a small tube, and everyone was having different flame speeds. which really proves that the flame speed was depending on the size of the tube. And if you would go to the limit in a very small tube, the flame speed would go to 0. So the flame speed actually increases with the size of the tube. And it took them, I don't know, it was around 1900. It took them a long time to understand what the problem was. Once they knew what the problem was, they were able to plot here the quenching distance as a function of equivalence ratio. And again, if you have a very fast flame, which is very thin, then the quenching distance is small. If you have a big slow flame, then you can have a larger tube. And you can see here the dimensions. 1 centimeter is big. I mean, that means really these flames here, for this equivalence ratio, which is a lean flame, this flame would not be able to propagate in a tube like this. It would stop. So why do we care? Well, there are 2 big applications for that. The first one is flashback protection, and the second one is mine lamps. So flashback protection is important for you if you do an experiment with premixed gases. If you here have premixed gases, and here you have a combustion chamber, the flame can flash back. I've shown you pictures. And one way to avoid that is to put here a grid with holes, and the holes should be less than the quenching radius. So this way, when the flame will arrive there, it will stop. So for example, for this film, that movie that you've seen before, if there would have been a grid like this here, the flame would have stopped. And some companies actually market this flame arrestor system. You have a plot on the right side. These flame arresters are just small tubes here with a small diameter so that if a flame arrives here, it will be quenched and it won't propagate on the other side. Just be careful, this works only once. When I did my PhD, we had a system like this with a grid here to stop the flame. So we operated for 2 years and then we took it off and then there was a hole like this in the middle. Because, of course, when the flame arrives on a small flame arrestor, it just burns it. So if you have a flame arrestor, you should check from time to time that it's still there. So otherwise, it's dangerous. Those systems are built exactly to do that. It's not difficult to build a flame arrestor. It's difficult to build a flame arrestor which resists many flashbacks. That's where the difficulty is. Now, the second application was mentioned before by Paul. I want to talk about it too because it's quite interesting. Once you know that you have the possibility of stopping the flames while letting the light go out, you can invent that, which is actually probably the reason why we are here, because when they started burning coal, if they wouldn't have had that, it would have been very difficult to operate these mines. So the problem is to have light, no electricity, okay? So you make a flame here. It's the only way you can have light in the mine, and to avoid igniting the mixture which is here. So the way you do that, you add this grid here. You can see the lamp here. This is the Davy lamp. And so the light is inside, and here you have this small grid which prevents the flame from going out. Okay? Great system. Now, just another thing I want to mention about that. Davy was a lord. Okay? In those days, things were a bit different. He was a lord. He took a patent on that. Then he wrote a paper on it. And then he found out that there was another guy called Stephenson in England too, who designed almost the same lamp. And that's, I've told you before, if you have an idea, a good one, someone's got it at the same time. And this poor guy, Stephenson, found it completely independently of Davy. But Davy went mad, actually. When he saw that Stephenson had found the same thing, he said, "You copied me, you stole it from me." And so he sued him. And Stephenson actually lost. I mean, people said, of course, if you find the same thing, it's because you stole it from Davy, which was not true. I mean, we know now that Stephenson just got the idea because it was the right moment to have the idea. But of course, if you're a lord, you win. So Davy won basically this problem, and then the poor Stephenson, I guess, died a little bit later, and he had no money. All the money went to Davy. So I want to finish by a small story, which actually two short stories actually. This one is a great one because it was mentioned by Paul too, but I think he didn't go to the end. It's all example of combustion sciences grouped in one example. So this is a mine tube, okay? And you know, in a mine you get coal, but you also get gas. Usually it's methane. This gas is lighter than air. If you have gas here, if you have enough gas, at some point someone's going to make something stupid and you're going to get an explosion. So usually in those days, the bosses were not like today. They would say if there is coal here, that's fine. If there is gas, it's your fault. So I'm not paying you until you find a way to clean this place. Because, of course, it's your fault that you have, made all these problems with my mine. If you have this kind of problem in the mine, the consequences, of course, are not pleasant. Okay? This is the one outlet here. When you have a mine shaft which gets ignited at one end, you see the kind of flames. No need to say that no one's going to survive that. And when you say no one survives, it's not a hypothetical problem. The numbers today are still thousands of people killed. China, for example, has a big problem with that. It's just a list here of the number of people killed. This is a very old drawing. This is a more recent picture, but these things kill people. Now, there are two ways you can fix a problem like that. I want to show you the bad and the good way. The bad way, of course, is that if you have gas in your mine shaft and it explodes, after that you have no gas left, obviously. But that's not a good solution. There is a good way to do that, is to use what we call controlled combustion. And what I'm going to tell you is not a legend, okay? They really did it. You can burn the methane slowly, and it's bringing us back to everything we've been saying about theory here. The gas in a mine shaft is light. It's usually methane. So it's going to go up. Okay. So if it goes up like this, you end up with a situation which I've described before. This is the mixing line in diffusion flames. You have a state here where you have gas on the top, air on the bottom. And I told you that if you are in this situation where you have gas on one side, air on the other side, it's not a very dangerous situation because it's the way you create diffusion flames. So if you let the methane go up and you let the air at the bottom of the shaft, you can imagine that instead of creating an explosion, you could create a small diffusion flame which would burn this thing. There's only one problem. Well, there are two problems. The first problem is to have the gas on the top, you should stop moving. Okay? No movement. As any convection movement here will mix the gas. So the first thing, you get everyone out of the mine shaft. And then you wait. The problem is if you wait, okay, that's fine, but you have the gas here and the air. And then remember, for combustion, you need gas and air and temperature. So someone has to go there and to ignite it. They did it, believe me. So how do you do that? Well, it's easy. you take a PhD, first year, so someone who didn't come here, and you give him a Davy lamp. You see, this is connected to the Davy lamp because the guy has to go far away to bring the ignition at that point. So usually he has to crawl. Why does this guy crawl? You crawl because you're at the bottom here, and normally at the bottom you have more air and less problems with gas. So you go there, the guy crawls for a few 100 meters, and he has this Davy lamp to see where he's going. But because it's a Davy lamp, the risks are limited because there's no ignition for the moment. And at the place where the fuel is, he just removes the grid from the Davy lamp and he raises his hand. Okay? They did it. I know. And so there are two solutions there. The first solution is that at the point where the guy is, fuel and air were really totally segregated. So you really have fuel here and air here. And there, when you do that, what you create is a triple flame. Remember these triple flames we talked about? Because here you have this famous state I described, which is the mixed state without combustion. And here you have the ignited flame. And so you will have like a sheet of flame propagating in both directions. Sometimes you see them in Hollywood movies. Near the ceilings, you see this big, when they simulate a fire, you see these big blue sheets, and they would look like this. And at each end of the sheet, you would have a triple flame propagating on both sides. And then for a moment, you would have a diffusion flame between the fuel here and the air here. And when the whole fuel here is exhausted, the flame would stop. So that's a very convenient way of completely evacuating the gases there. Then, of course, there's a second solution. If fuel and air are not fully segregated, then you will ignite a fast premix flame and you will have an explosion. But you will notice that in every case, you can start operating again. So that's the way people thought in those days. And it's actually, I found quite a few documents showing that it works, but they would really do it like this. Okay, let me conclude here by a small, another short story, because I think I'm almost done now. I just want to insist on something. I've shown you a lot of movies, okay? But I want to tell you one thing which I'm a little bit afraid of. And so it's what I call Combustion life in 2025. So in 2025, we would have been so successful with simulation. It would be your generation. I will be retired probably. That we can solve everything with numerical methods. So we just get a very new problem I'm going to present in a second. And we said we're going to solve an equation which is really puzzling and really complicated to do. And to that, we're going to have brilliant PhD students, of course. And the new code we have will be 18th order, Joule injected. And we're going to have a machine costing $200 million. And we're going to need, probably a big system and a lot of money. And you see this interface here, which says, please compute geometry. And probably there will be also something to write my PhD, please. You can talk to your phone and it will do that. Now, the thing is, what do we want to solve? Well, there are three phases for this big program. And the budget is about $40 million. And the equation you need to solve, I hope you're not too afraid, is this equation, okay? That's a tough one, okay? So obviously it's going to take a while. So the first year, we've solved this equation for A equal 1, B equal 3, C equal 1, and we have one solution. We believe it's that. But so that really proves that our code can do it, okay? So we asked for an extension, $20 million more. And then one of the PhD students comes back and he says something strange happened. He could not find any solution for 1, 2, and 4. And so we had more needs for more CPU time. And it's true that we cannot find a solution here. So that proves we need more money. So after 9 years, it's strange because we tried to write papers, but it seems no one wants to publish them. No problem. We keep working on that. We found a case where the solution of this equation is not one, but two solutions. So probably there are cases where there could be more than two. Could be 3 or 4, who knows. So we need more money to do that. And so the real question about all this is, how long will we take before we understand that A doesn't play any role, that only the ratio B over A and C are very important? Well, the answer is, how long before someone says there's an identical solution? Well, never. If we keep running the code, we will never do it. So in other words, computing makes people stupid, okay? So that's if you go this way, if you start running codes, and I see a lot of people around here came to me and say, I'm running this code to do that. Well, I would stop running the code, think about the problem, okay? Don't run the code. It's not your first problem. And I know at that point that my students actually told me, well, that's a good joke, boss, but that won't happen to us. I mean, well, it certainly happened to me. When I did my PhD defense, there was a famous guy called Barrère, and he told me, you spent 3 years to show that the criterion of stability should be that the combustion delay is more than the acoustic period, half of it. But actually, he found it in 55, I mean, in 3 pages. And actually, after he told me that, it's in my book now, I said, in 2 pages, you could recover what took me 3 years to do. So you really need to make sure that when you do something, there is no identical solution first. There is no way of showing that what you're doing is not needed. And if you get a result, you should check that it makes sense. And I really see a big problem at the moment. I see people running codes everywhere. You've seen nice pictures, okay, nice movies, all that. But please don't do that only. If you just run the code, you're lost, okay? You need to get the theory running. The code is telling you something about the flame speed. You need to check if that makes sense. Telling you something about the adiabatic flame temperature, go look at theory. Don't just run codes. So that would be my conclusion. I've shown a lot of nice movies. Don't believe those things are real. You need to learn theory for you so that you know what's going on, and don't rely on codes to help you for that. Okay, that'd be all for this school. I wish you good luck. Well done.